Hello everyone, here is a question based on coordination complexes. The number of paramagnetic complexes among the following which involved D2sp3 hybridization is how many? Paramagnetic complexes means we should have unpaired electrons. So in each case we need to figure out the number of unpaired electrons, and also the hybridization has to be D2sp3. This means it has to be an inner complex. If it is an outer complex, then we need to ignore that. What we mean by inner complex is it has to use the 3D orbitals. So this D2sp3, it has to use the 2 orbitals of 3D instead of 4D. So let me write it this way. So let's say this is 3D and then 4s and then 4p. So if the hybridization is this way, D2sp3, then we can say it is an inner complex. On the contrary, if the hybridization is this way, 4s, 4p and then 4d, sp3, d2, then we have to call this as outer complex. This is outer complex, this is inner complex. Now, before going into those things, first of all we need to determine the oxidation state of each metal ion. So I will do it for one and then I'll tell you what is the oxidation state for the other cases. So we have FeF6 3 minus, the net charge is 3 minus in each case. Let's put the oxidation state of Fe as X, and then the charge we give for fluorine is -1. We have 6 ligands, so therefore 6 times -1 and that is equal to -3. Therefore x minus 6 equal to -3. This means x is equal to +3. So therefore the oxidation state of Fe in this case is +3. Now if we work it out for all the complexes, you will find that the oxidation state is +3. You can work it out because for cyanide it is -1. So here also the net charge is 3 minus. You will get +3 oxidation state in every case. For oxalate ligand we give -2 as the charge, but we have 3 ligands. So likewise in every case you will get +3 as the oxidation state for the metal ion. Now we know that F minus and Cl minus are weak field ligands and cyanide is the strong field ligand, and oxalate normally it is considered as a weak field ligand, but here we have to consider oxalate as a strong field ligand. Why? Because the oxidation state of the central metal ion in this case is 3+. So this means that when a metal ion is in a high oxidation state like +3 for cobalt, its attraction to the oxalate ligand is stronger, causing a larger splitting of the d orbitals and making the complex low spin. So therefore we have to consider oxalate in this case as a strong field ligand instead of weak field ligand. Now I'm going to use CFT instead of VBT because VBT doesn't tell exactly to what extent we need to do the pairing and all. So therefore CFT is the best choice to use, and depending upon whether it is a strong field ligand or weak field ligand, we can think about the hybridization and we can find out the number of unpaired electrons. If we have number of unpaired electrons, it is paramagnetic. If all the electrons are paired up, then it is diamagnetic. Now here Fe is in +3 oxidation state. So therefore the electronic configuration is argon and then 3d5, isn't it? Because when it is neutral, we have 26 electrons. At that time the electronic configuration is argon, that has 18 electrons, and then 4s2 and then 3d6, that is when it has 26 electrons. But now we don't have 26 electrons, we have only 23 electrons, because when it is +3 oxidation state we will have only 23 electrons. So therefore the 4s2 electrons will be removed because n value is equal to 4, that is in the outer shell, and then 1 electron from 3d6 will be removed. So therefore the electronic configuration now is argon, and then 3d5. 18 plus 5, 23 electrons. So 5 electrons are there in the d orbitals in the free ion. When the ligands approach, fluorine is a weak field ligand, and therefore the crystal field splitting energy is less than the pairing energy. This means that pairing won't occur. So therefore, the metal ion has to use the outer shell orbitals for hybridization. So therefore, the hybridization is 4s, 4p, and then 4d. These are the orbitals that will be used for hybridization. 2 orbitals from 4d will be used. So this means the hybridization in this case is sp3d2. So even though the complex is paramagnetic, because we have 5 unpaired electrons, the hybridization is sp3d2. Therefore, we shouldn't count this complex. Let's go to the next one. Here too, Fe is in +3 oxidation state. Therefore, the electronic configuration is once again argon and then 3d5. We have 5 electrons here. However, cyanide is a strong field ligand. Therefore, the crystal field splitting energy is greater than the pairing energy. This means pairing will occur. So this means we will have only one unpaired electron, n equal to 1. Therefore, it is paramagnetic, and therefore 2 of the 3d orbitals are available for hybridization. So 4s, and then we will have 4p. So this means the hybridization in this case is d2sp3. Therefore, we should count this complex. How about the next one? Next one, manganese 3 plus, atomic number is 25, but when it is 3 plus, we will have only 22 electrons, and therefore the electronic configuration is argon, that has 18 electrons, and then 3d4. So we have 4 electrons in the d orbitals in the free ion, but cyanide is a strong field ligand, and therefore pairing will occur, and we will have 2 unpaired electrons. N value is equal to 2 here. We cannot pair up this one also. If we do that, then we are violating the Hund's rule, isn't it? So we cannot do the pairing that way. Therefore, we need to have 2 unpaired electrons in this case. Now, when we do with the VBT, there is a chance of making that mistake. That's why I said I want to use CFT to solve this problem. Because by mistake, if you are pairing up all the 4 electrons and writing it in 2 orbitals, then you will have 3 orbitals available. That's not how it should be. Okay. So here too the hybridization is d2sp3. So therefore we should count this one too. It is paramagnetic because we have 2 unpaired electrons. How about the next one? Next one, the oxidation state of cobalt is 3 plus. Atomic number of cobalt is 27. But when it is 3 plus, we will have only 24 electrons. And therefore, the electronic configuration is argon and then 3d6. 18 plus 6, 24. So we have 6 electrons in the d orbitals. We have to consider as a strong field ligand because of the metal ion having a higher oxidation state. We have to consider oxalate as a strong field ligand, and therefore pairing will occur. So this means that we will not have any unpaired electrons here. Therefore, this is diamagnetic. The hybridization is d2sp3. However, we shouldn't count this because it is a diamagnetic complex. How about the next one? The next one, manganese 3 plus, the oxidation state is, we have 22 electrons when it is 3 plus. Therefore, the electronic configuration is argon and then 3d4. We have 4 electrons in the d orbitals in the free ion. That means in absence of ligands. So in presence of ligands, it is a weak field ligand, and therefore pairing won't occur. So this means that for hybridization, the metal ion will be using 4s, 4p and 4d orbitals. So therefore the hybridization in this case is sp3d2. Even though the complex is paramagnetic, the hybridization is not what we wanted, and therefore we shouldn't count this. And then finally we have COF6 3 minus, oxidation state of cobalt here is plus 3. So that means we have 24 electrons once again. Therefore the electronic configuration is argon and then 3d6, 18 plus 6, 24. So 6 electrons are there in the d orbitals. Fluorine is a weak field ligand, and therefore 1, 2, 3, 4, 5, 6. We have 4 unpaired electrons. It is paramagnetic, but what would be the hybridization? Hybridization in this case will be once again sp3d2, and therefore we shouldn't count this. So this means only 2 complexes are having d2 sp3 hybridization with the paramagnetic behavior. One is this one and another is this one. Therefore the correct answer is 2.